So in the previous session we have studied about source of voltage in solar cells. In current session we are going to see efficiency of solar cell, or we will describe detailed valence limit or SQ limit. So let us begin. So irrespective of solar cell configuration, its material, its device configuration, the physics behind solar cell working. So a solar cell requires 3 steps to be taken place for efficient working. So it is irrespective of what, whether it is organic, whether it is hybrid, or whether it is inorganic. Okay. So 3 steps which are required are absorption, separation and collection. So absorption, if you see in a 2-level system, so you can see simple semiconductor which has a 2 levels, conduction band and valence band. So we are calling it 2-level. So in this 2-level system which has some band gap, okay. Now in this system what will happen, whenever a photon is being absorbed, photon strike, electron hole pair generate, and there is separation of electron hole pair, a generation of electron hole pair. So this changes the dynamics of, or the statics of carrier dynamics. So absorption lead to the unequilibrium condition, okay, and generation of your quasi-Fermi level. So this we have seen in our last session, okay. So this absorption must take place, and the change in quasi levels, the change in quasi-Fermi levels must take place. First thing. Second thing is separation. So what is separation? So this generated electron hole pair, which is a bound electron hole pair or exciton, so it need to get separated. So there are some ways to do it. So if it is organic, there is a one mechanism. If it is inorganic, there is another mechanism. So there is a couple of mechanisms depending upon the material. Okay, depending on the material, the separation mechanism may be different. So you can see this is PN junction. So this is inorganic. Say for example gallium arsenide, for example silicon solar cell, for example CDT solar cell. So those kind of PN junction solar cells, this is the mechanism by which separation of electron hole pair take place. So you can see here we have an electron hole pair, and at the PN junction, so at a junction we will have a depletion region which has a band bending. Okay, so band bending will provide an inbuilt electric field for electron to follow, okay, and then electron hole to follow in opposite direction. So this way they get separated in your PN junctions case, okay, PN junction solar cell case. Now the other mechanism is say your mobility junction. So you can say example your perovskite with ETL and STL layer. So you have an observer perovskite layer, and the ETL layer will have a huge electron mobility. So any electron hole pair which is near to this junction or in the vicinity of this junction, electron hole pair ETL junction, so that electron will get transferred to the ETL layer with huge mobility. Okay, so electron will transfer hugely, move with high velocity in the high mobility in the ETL layer. Similarly the case with STL. So whenever electron hole pair come in the vicinity of STL and observer junction, so that hole will get separated because of the high hole mobility. So it is basically filtering out. So this is again a second mechanism, okay, for a separation to take place. The third mechanism is your force field. So force field, you can see in this case you can see donor and acceptor. So in case of organic solar cells, you have a donor and acceptors. So you can see there is a difference between there's a difference between the conduction band levels and the valence band level. You can see there's a difference. So this difference is providing us the difference is occurring due to the different work function or different electron affinity of the different donor and acceptor material. Okay, so this exciton bound electron hole pair, whenever it comes this exciton come into the vicinity of junction, electron and hole get separated due to this excess energy. You can see this excess energy. So this is acting as a separator. Okay, so this mechanism you can find in perovskite solar cells or in organic solar cells. Okay, so these 3 different mechanisms are there. So these 3 different mechanisms are there which are electric field dependent, or mobility junction dependent, or force field dependent for separation. Okay, so the third step, which is collection. So collection, now after the separation, now you need to collect the generated electron hole pair. Okay, so this can be done by having a near ohmic contact or ohmic or near ohmic contact. We require ohmic contact for this separation to take place. So you can see this can be achieved by generating highly doped region near the contacts. Okay, so you can, if it is a p-type semiconductor, you can have p++ layer, or it is an n-type semiconductor, you can have a n++. So higher doped region. Okay, so that particular contact region can be highly doped so that near ohmic contact can be achieved. The second mechanism is by having high work function contact. So you can utilize those metals which have a high work function to get near-ohmic contacts, particularly with p-type material. So you can have nickel, you can have gold, you can have platinum as a contact material for efficient collection. Okay, so this is now these three steps complete the overall working of solar cell device. Okay, now for the efficiency to understand efficiency, we must know what is the input power coming in and what is the output power generated by a device. Okay, the ratio of these two will be known as efficiency for whatsoever thing. Okay, so in our case, if we see the input power is this solar spectrum, so this is shown in the solar spectrum. In this we are getting different photon of different energy. Okay, so photon of different energy we are receiving. So if our two level system is shown here with band gap Eg, so this will correspond to say 1 electron volt energy or 1240 nanometer wavelength photon, which is corresponding to 1 electron, corresponding roughly equivalent to 1 electron band gap energy of the photon. So if this photon strike to this semiconductor, it will be perfectly absorbed. Okay, so green color, you can see by a green color photon is perfectly absorbed. Suppose if the photon has a energy less than this band gap, less than this energy, or of higher wavelength, so 1500 or even higher wavelength, or less energy, less energy than this particular band gap. So what will happen? This photon cannot make a transition of electron from valence band to conduction band. So this photon is non-absorbed. Okay, so all these photon below 1 electron volt or of higher wavelength energies, then they are they are passing, they are not getting absorbed. Okay, and if the photon energy is greater than the band gap energy, as in the case blue photon, you can see it has a higher energy or a lower wavelength. So what is happening here is part of energy is getting going waste. So that part you can see this greater than, or this higher energy photon energy more than Eg, more than the band gap, is getting lost in warming up the lattice. So it is like relaxing. So it is transferring its energy to the lattice and getting getting the whole material heated up. Okay, so lattice temperature is increasing, but that is not getting converted into electron hole pair. So that is basically going waste. Okay. So now we have seen two losses: the thermalization loss, nanofiction loss. We have already seen. So what our input power, what is the input power we have now? There are some losses, and the only useful power is this green color photon, which is perfectly absorbed, and part of this high energy photon, part of that high energy photon, that is being our useful power. Okay, there are other losses also. So what are those losses? We can see. I will tell you why this way. That this particular region, this particular dashed region, this particular dashed region, shaded region, you can see this is the region which is useful for us. Okay, and the region which is blue color region, there is thermalized loss, getting lost in heating up the lattice, and the red color triangle which is showing the non-absorbed photons region. Okay, so only this part, whitish part, is being useful for us, whereas there are losses into this white color region also. So what are those losses? We will see. So you can see out this two level system. So you have a thermalization loss, blue color, you have a red color non-absorption loss. Okay, and the perfect absorbed is green color. Now you are having radiative recombination shown by a blue triangle, downward blue triangle, which is radiative recombination. So for any material, if it is not at absolute zero temperature, it is in constant exchange of energy with its surrounding. Okay, so this is the fact. So this is the intrinsic loss. So it cannot be avoided. This loss will take place. So radiative recombination loss will always take place depending upon what temperature the device is. Okay, so radiative recombination will always take place. So that is emission loss. Okay, and then this is non-radiative recombination loss. So non-radiative recombination loss may arise because of some you have some say recombination site in your material. If the material is not pure, if you have some defect in the material, non-radiative recombination can arise by that. Okay, and now we have some other losses. So you can see we have Eg is the band gap, and there are EFC and EFV. So quasi Fermi levels are being shown. So that is generating the useful energy, the difference between EFC minus EFE, that is our useful energy, it is less than the EG. So the remaining part is going lost as other losses. So what are those losses? So if I give you a description, what are those losses? So we can see out that radiative recombination loss is the emission loss, which is intrinsic one. The other losses are radiation dilution loss. So that is whenever energy is changing from one form to another. Okay, so there is a energy change is taking place, and there is a second thing is if the change is irreversible, then there is a generation of entropy. So taking these two into account, they said that is what causing us our solar cell output V voltage. Say if the solar cell output is V voltage, so V will always be less than the EG. So that's why that is basically because of these three losses: emission loss, entropy loss, and energy conversion loss. Okay, so if for ideal condition we can take non-radiative recombination loss to be 0, because we are calculating out only the intrinsic losses. Okay, intrinsic losses which cannot be avoided. So thermalization loss taking place, nanofiction loss is taking place, radiative recombination loss is taking place, other losses comprise of entropy generation. That is, so whenever entropy generating, some portion of our energy is getting waste there, and energy conversion loss. So energy conversion from hot body to cold body is taking place. Okay, so I will explain the energy conversion and entropy loss in due course of time. Okay, so this is the overall picture, like detail balance limit. Okay, so now if I calculate out what is what percent, let us see. So you can see out in two-level system. So in two-level system we have our thermalization loss, our nanofiction loss, and our other losses, and along with it radiation losses, radiative recombination losses. So what is the input power? So input power is full spectrum, whatever the spectrum is. So spectrum function is phi E. So phi is our spectrum function. So you can see out in this here. So this is our spectrum. Okay, so a function defining these all wavelengths along with their energy. So this is our spectrum function. Okay, so this phi is our spectrum function here, and E is the energy of each photon, with each photon energy E, and photons either you take in terms of energy or in terms of wavelength. So we are taking here in terms of energy. So 0 to infinite energy. So photons of all ranges, from 0 to infinite energy ranges. Okay, so this is our input power. So summation of all energies of all the photon available. Okay, so that is our input power. Now what are our losses? First loss is our nanofiction loss. So you can see nanofiction loss all are those photons which are less than the band gap energy. Okay, so 0 to EG. So 0 to EG photons are not absorbed. So either the photon should be EG or above EG, and then only that photon is absorbed. Okay, so this is 0 to EG, and E the energy of photons, and the photon spectrum. Okay, E phi E. So that is none of the photon part. Now the third loss is thermalization loss. So thermalization loss is energy of photon minus EG. Minus EG, that is the lost part. EG is the utilized part. Okay. Now suppose if the energy of photon is more than twice the band gap or thrice the band gap, then in that case, whether the photon is generating only 1 electron hole pair or two electron hole pair. So in some certain special cases, it can happen that high energy photon generate two electron hole pair. So that can take place. So that's why we have taken gamma. So gamma is a function like number of electron hole pair. So generally it will be 1. So if it is 1, then E minus EG, that the lost part for complete spectrum from EG to infinite. Okay, so that is our thermalization loss. Now the third part is radiative recombination loss along with other losses. So those losses are first the recombination loss. So V is the voltage at which cell is working, into JR is the recombination current which is flowing into the device, and that's the one part. Second part is EG is the band gap of the solar cell, which is like which should be the ideal case, but it is not giving at EG, it is not working at EG, it is working at V. So E minus V is the energy which is not taken by us. Okay, so E minus V along with gamma E. So gamma E is again how many number of electron hole pairs. Okay, from EG to infinite. Okay, so this is again complete complete other losses. Okay, so if we plot these three losses, then so P in minus these three losses is what our useful energy is. Okay, so that is our useful energy is. So this all are band gap dependent or energy dependent. So we can see out the plot. So thermal action loss, you can see it is depending upon the band gap. So at the higher band gap, this is going decreasing out. Nanofiction loss at the higher band gap, it is maximum, and this radiative recombination loss along with none other losses, you can see out this is also a band gap dependent loss. Okay, so somewhere our utilized function, our useful work energy, this is being maximized at some certain band gap, say around 1.2 or 1.3, which is the SQ limit. So this is what the SQ limit is, which comes out to be 33% for a two level system, for a single band gap. Okay, this is what the detailed balance limit. Okay, so the conclusion here is the losses are limiting single junction to 33%, which is known as SQ limit. To avoid it, to overcome these losses, we have to like decrease out these losses, thermalization loss, nanofiction loss, or other losses. Okay, so one can go to our playlist, SCAPS training lecture series playlist, and there session 23 one can go and one can see out how to at what band gap, what are the parameters, what are the efficiency, all those parameter can be seen, can be like plotted using SCAPS. Okay, so that's all for today. So in next session we will see about how to overcome SQ limit.